homework, I think it's question number 5. So this is homework 02. Okay. Question number 5. And I see that it's the geometric analysis that you all have problem with, which I did talk about in last week's tutorial. Okay, I did mention about this in the last week. Now, anything, just stop me. This is a tutorial, okay, like lecture. You can stop me anytime or type something. If I don't see the chat, I see I'm going, let me know someone type a question, okay? So from here, okay, what we are given is we have a gradient distributed load, okay, and determine the reaction at the support, okay, and given that the diameter is 120 millimeters and unloaded origin, the length is 1.4. Take the Young's modulus of wood. Okay, so let's compile what we have first. Okay, now I deliberately put the solution manual down here because it can help me in looking at our checkpoint. Okay, I'm not going to try to figure out what they're trying to do. No, don't do that. Okay, don't figure out what they're trying to do. I'm not going to say, what is step 1? Oh, step 2. Oh, step 3. Step. No. Just apply what I teach you. Most important thing. Okay, that's the most important. Okay, so we know from here, right, given those information, so we know that we're going to find area of A is equal to area of B is equal to area of C. Okay, so we are aware that this is pi and this is 0.06 squared. Okay, so we find the cross-sectional area first. So 0.06 squared times by shift pi is 11.31 times 10 to the power minus 3 meters squared. Okay, I will do it again. 0.06 squared times by shift pi 113.09 times 10 to the power minus 6. Okay, so the next one, we know that the Young's modulus of the wood is 12 times 10 to the power 9 Pascal. Okay. So the next thing that we're going to draw is we're going to construct our multi-body, okay, multi-body. Free body diagram. Okay, so we label our transformation X, Y. This is rotation about Z. Okay, so I'm going to put down so this is our point A, point B, and point C. Okay, and then I'm going to draw our member down here. 1, 2, and 3. Okay. Now, question for you: the wood portion of A, B, and C will it be, or where is 0.06 come from? So 0.06 is because the diameter is 120 millimeters. Okay, so I take 60 millimeters. Okay. So A, B, and C, right? The support A, B, and C. Do you think it will go into compression or tension? Anyone?
Should be compression.
Yes, you're absolutely right. It will go onto what? Compression. So you just go compression. Right? They will all go into compression. Okay. And then remember, I taught you guys, I think this is week 1, action equal reaction, same in magnitude, different in direction. So this will be in opposite direction. So this is your F, or okay, I call it AY. Okay, your BY and your CY. Okay. Okay, so this is one part. You have to get it. You understand that everything goes into what? Compression. This will give you confidence on your free body diagram. Okay, you will know why it's going this way or not. You will not have I'm not sure. Is it going up or is it going down? I don't know. I don't know. This will make you very, very sure. Okay. Then the next thing is you have a triangular load over there, right? And a triangular load, again, this is from week 1. Okay. So this is our equivalent load. Okay. So this is equal to half. The base is 3. And the height is 18 times 10 to the power 3. Okay. Because it's triangular. Okay. So 0.5 times 3 times 18 power 3 is equal to 27 times 10 to the power 3. And where it is acting on, okay, again, this is lecture from week number 1. From here to here is 2 meters. From here to here is 1 meter. Now, how do we get it? We know that this is 2L over 3. And this is L over 3. And the entire length is what? 2L. So the length is 3. So 2 times 3 divided by 3 is equal to 2. And this one is 3 divided by 3 equal to 1. Because L is equal to what? 3. Okay. So if you look at week 1 lecture, we have the same load distribution down here, right? And it's only in different direction. And I did explain to you like how to find the equivalent load. I just apply whatever I show you down here. Nothing new. Okay, nothing new. Okay. So from here, right, now we have everything already. Now we can do our static analysis, right? From here, we can do our static analysis. Okay. So static analysis. For members ABC. Okay. So we are going to do summation about moment in the Z direction at point A. We're going to take moment about point A, the whole thing is equal to 0. Okay. So we have 2BY is going anti-clockwise plus by 3CY is also going anti-clockwise. Then the equivalent load, the 27 times 10 to the power of 3 is going in anti-clockwise, so minus 2 times by 27 times 10 to the power 3. The whole thing will be equal to 0. Okay, so I check 27 times 10 to the 3 perpendicular is 2. So 2BY plus 3CY is equal to 27 times 2 is equal to 54 times 10 to the power 3. This is our equation number 1. Okay. Then the next one, we are going to take summation about forces in the y direction. The whole thing will be equal to 0, right? So this is equal to AY plus by BY plus by CY minus by 27 times 10 to the power 3 is equal to 0. So you form AY plus BY plus CY is equal to 27 times 10 to the power 3. This is your equation number 2. Okay. So we have 2 equations, 3 unknowns, right? We are able, using static analysis, right? Using static analysis, we have 2 equations and 3 unknowns. Okay, so this is where the structure is statically indeterminate. Okay. So the next thing that we do, we are going to look at elastic. We're going to do analysis. Okay, we're going to do an analysis based on elastic deformation. So we know that the formula is equal to delta is equal to PL over AE, right? Tensile is positive, compression is negative. We know that. Okay. So now we're going to find that deflection at point A. So I'm going to copy the diagram. So we can see the diagram while working on it. Okay. In fact, there's not a lot to watch. So deflection at point A is equal to AY. So it's going to be compression minus AY. L is 1.4. Cross-sectional area we calculated, I think somewhere at the top that we calculate is equal to 11.31. Okay, 11.31 times 10 to the power minus 3. E is the E that we use is what? Let me see. The E is 12 times 10 to the power minus 9. Okay, so it's 1.4 divided by 11.31 power minus 3 divided by 12 power minus 9. Okay, it's equal to 10.315 minus 10.315 times 10 to the power 9. Okay, AY. I'll do it again. 1.4 divided by 11.31 power minus 3 divided by 12 power minus 9. Why minus 9? Plus 9. I do apologize. 1.4 divided by 11.31 power minus 3 divided by 12 power 9. Why minus 9? Okay, so 10 times 10 to the power minus 9. Okay. So 1.4 31 power minus 3 divided by 12 power 9. Okay. So then we're going to look at deflection at point B. Okay. So because the cross-sectional area is the same, the length is the same, the Young's modulus is the same, the only thing that changed is the forces. So this is By. And deflection at point C is equal to minus 10.315 times 10 to the power minus 9. This is Cy. Okay. So now we have deflection of A, deflection of B, and then deflection of C. Okay. So next we have to link. So equation 7. No, not equation 7. This is 1, 2, 3. Okay, equation 3. Equation 4. Equation 5. Okay. So the next one is we have to link. Okay, relate equations 3, 4, and 5 into one equation. Okay. Because now there's no relationship with AY, BY, and CY at all. Okay. So we have to link them. How we're going to link them is through geometric analysis. Okay. Okay. So this is basically based on positioning during deformation. Okay. It's just positioning based on deformation. So I'm going to copy the diagram again. Okay. So now we are going to assume A, B, C are rigid body. Okay. Now, the next thing is, how will the structure deform? Okay, how will the structure deform? So we know that